Have you ever just stopped and wondered, how does a skyscraper actually stay standing? Or how does a satellite stay perfectly in orbit? How is this smartphone you're holding in your hand even possible? Well, behind pretty much every complex piece of technology we use, there's this invisible architecture, a kind of master plan. And today, we are pulling back the curtain on that plan. We're talking about systems engineering.
So, to really get what this master plan is all about, we first have to appreciate the kind of chaos it was designed to control. Let's start with the huge fundamental problem that systems engineering was literally invented to solve.
I mean, it's the question that keeps engineers and project managers staring at the ceiling at 3 a.m. We've all heard the horror stories, right? The billion-dollar software that just never launches. The bridge that's years and years behind schedule. Why is it that the bigger the ambition, the more likely it seems to end in disaster? The answer, really, boils down to one word: complexity. See, as you add more parts, and more people, and more goals, the number of things that can go wrong doesn't just add up, it multiplies, like exponentially. Without a really good map, you're absolutely guaranteed to get lost in that jungle of details.
And this is exactly where systems engineering comes in. It's not about designing one tiny little part. It's the discipline of designing the entire thing as a whole. It gives you the structure, the framework, and the process to bring order to all that chaos. It's what makes sure all the different pieces actually fit together and that the final product does what it's supposed to do.
Okay, so if systems engineering is all about designing the whole thing, how does it even begin to do that? Well, it starts by taking a really, really long view. It doesn't just think about getting to the finish line, it thinks about a system's entire life, from the moment it's just an idea all the way to its retirement. And this is a core, non-negotiable principle of the discipline. You have to plan for everything. Seriously, how are we going to manufacture this? How are people actually going to use it? What happens when it inevitably breaks? And hey, what are we going to do to safely get rid of it? Maybe decades from now. All of these questions are on the table from day one.
This timeline here does a great job of showing that whole journey. Every system, whether it's a car or a software app, goes through these stages. You've got the concept, then development, production, utilization, and support, and then finally, retirement. Systems engineering is the thing that weaves a single, coherent plan through this entire timeline.
Now this quote, this one is so important because it gets at a critical point: the unbelievable weight of those very first decisions. The choices you make way back in the concept stage, what materials you're going to use, what core architecture you're going to follow, they basically set the course for the entire project. And a bad decision right here at the beginning can be ridiculously expensive, if not totally impossible to fix later on.
So, how do you make sure you're not heading down the wrong path? Well, you use something called decision gates. You can think of these as these really formal, high-stakes meetings. At the end of each big stage, everyone who matters gets in a room and looks at the hard evidence. Is this project still viable? Are we hitting our goals? Do we keep going or, and this is the hard part, do we pull the plug before we waste any more time and money? These gates are basically the safety valves that prevent total catastrophes.
All right, so we've talked about the big picture timeline and the checkpoints along the way. Now let's zoom in a little and look at the actual blueprint, the technical stuff that turns a vague idea into a real thing.
At its heart, the process really follows this kind of path. You start by getting a deep, deep understanding of what the stakeholders, the customers, the users, anyone with a vested interest, what they actually need. Then you have to translate those needs into super precise, testable requirements. From there, you design the system's architecture, its high-level blueprint. And finally, you build the pieces and test them against those requirements you wrote. This whole process makes sure you're not just building the system right, you're building the right system. There's a huge difference.
But here is the really crucial part. This isn't some simple one-way street. This process happens again and again and again at every single level. You do it for the entire airplane, then you do it for the wing, then you do it for the engine on that wing, all the way down to a single bolt. It's this constant cycle of defining, building, and testing, and it's all happening at the same time. It's pretty wild.
Now, having a technical blueprint is absolutely essential, but it's not enough to keep a massive project from just veering completely off course. That's where you need project guardrails. These are the management processes that are designed to keep everything on track.
And a huge part of this is just managing uncertainty. So risk management is basically like proactive pessimism. It's about constantly scanning the horizon, looking for icebergs. But on the flip side of that coin, you've got opportunity management. This is about looking for favorable wins, new technologies or processes that could make the project even better, or faster, or cheaper. It's a two-sided coin, always. Okay, another one of these critical guardrails is called configuration management. Now, I know it sounds a little dry, but I promise you, this is the bedrock of sanity on any complex project. To put it simply, it's basically version control for everything. Not just software code, but for the requirements, the design documents, even the hardware parts. It's how you make sure everyone is working from the same set of plans.
And the benefits are just massive. It gives you one single source of truth. So the team building the engine and the team building the fuselage are using the exact same up-to-the-minute design. It tracks every single change, so you have a complete audit trail of the entire project. I'm telling you, without this discipline, you just get chaos, you get errors, and you get tons and tons of expensive rework. So, after looking at the life cycle and the blueprint and the guardrails, what's the big takeaway here? Let's try to put it all together.
When you really zoom out, you start to see that systems engineering is this hidden but absolutely essential discipline. It's really a shift from just designing things to designing successful outcomes. It is the reason our world of incredibly complex technology works as reliably as it does. It's the connective tissue holding everything together, all the way from concept to retirement.
And it's so important to remember that this isn't just about processes and diagrams. It is a deeply human, deeply collaborative effort. You see, systems engineering provides the technical blueprint, while project management is handling the schedule and the budget. They have to work together in what this calls a shared space to guide the whole team towards success. So, the next time you use your phone, or you board a plane or stream a movie, just take a second. Think about the thousands, maybe millions of invisible decisions, the trade-offs, the risk analyses, the life cycle planning that had to happen perfectly for that piece of technology to feel so simple in your hands. What hidden engineering is making it all just work?